So in this video, we're going to build on the concepts we learned in the previous video based on speed control, and we're going to see how we can achieve the torque speed profile that we've discussed in the past for the vehicles. So we're going to now translate. We're going to go from our machine to our vehicle, and we're going to see how can we get our machines to give us what the vehicle needs for the most efficient way means of operation. So you'll see that we'll be able to establish a similar profile as the one we have for the vehicle's torque speed characteristic using the models that we have for the DC machine. So now before I continue, I should mention that every variable you see with the subscript B in this video and onwards, I should say, I guess this applies for everything, is the rated version of that value. For instance, if you see omega B, it's the rated shaft speed. If you see TMB, that's the rated shaft torque. Because we're going to start working with ratings, because now we have to consider practical systems versus just some conceptual ideal type of situation. So now we'll have ratings, and we'll have to consider operating points as certain percentages of ratings. But more on that later. For now, we're going to start, and we're going to begin with the assumption that we have a mechanically ideal machine with no rotational losses, that the shaft torque and the power are equal to the developed torque and power respectively, and we're also going to imagine that the mechanical losses can be lumped with the resistance. So if we assume then that the flux constant is forced to follow given profile, we can begin our discussion of how to make everything cater to what we need, I guess. So let's start with the assumption that K phi is equal to K phi B and K phi B over omega M over omega B. And again, this is omega M as some fraction of the rating, right? So again, we're going to look at all of these things relative to the rated values, but we'll make things look a bit more pleasant as we develop our models. So this is true here, and essentially what you have in this situation is you can say that this is nothing else but K phi being equal to EB divided by omega B, and this is EB divided by omega M, and EB is the rated EMF, and this is for omega less than omega B, and this is for omega greater than omega B. Okay, so this, I mean, again, normalized shaft speed is what we refer to this as, but I mean, it's not that important because we can lump it in with another term and turn it into something else, so that's convenient. So since the resistance RA is small in a large machine, you can say that VA is approximately equal to K phi omega M, and we've made this this simplification in the steady state before, which means that this is EB over omega B times omega M, and this is for omega M less than or equal to omega B, and this is for omega M greater than or equal to omega B. Now, since we can't control K phi directly, well, actually, let's go back one step. Let's not jump ahead yet. So, what's the implication here? The implication here is that the armature voltage does not increase beyond the rated value of the EMF, even if you increase the speed, right? So you see here that the rated EMF is EB. So it doesn't matter what you do. In the ideal case, if you increase your speed further, the EMF or the armature voltage is fixed at the rated EMF. Now this is good because you have power supply limitations in practice. So if you know that regardless of how you increase your speed, your voltage will always be a certain fixed value. That's good because your supply won't need to be beyond a certain rating, right? So if it's 100, you know EMF is always going to be 100. You can have 120 volt supply. You're always happy. You know it'll never go past 100, so you're good with 120. However, in practice, VA is slightly larger than EB because of the winding, and the larger the winding, obviously, the more voltage drop you would experience across that winding resistance, and that would produce a larger armature voltage. Still, in practice, it's usually small. So this idea, the method of control that we're going to use is the one that we saw in the previous video, which is referred to as field weakening, since beyond the rated speed, we're going to decrease the flux of the machine. So why don't we then take a look at the machine shaft torque, right? So the machine shaft torque is Tm, and this is equal to K phi Ia. And since K phi is different in these two regions, we can say that in one case this is EB over omega B times Ia, and this is for omega m less than or equal to omega b. And in the other region it's EB over omega m times Ia, and this is omega m greater than or equal to omega b. This is our torque characteristic as it's related to the armature current. So that means for a given armature current, the torque is constant as long as the machine operates below its rated speed. So this is a constant as long as Ia is constant, of course, because these two are constant. Now in this case, it'll change, obviously. So beyond the rated speed, the torque decreases inversely proportional to the operating speed, which is something we've already seen that we actually want our vehicles to do. So it's a good characteristic for us to have. So overall, we can say that the tractive torque is proportional to and is controlled by Ia. Okay, so the shaft power as extension of this, and so we're doing in this video is we're tying all these concepts together. So the shaft power is EB Ia omega m, right? So this is omega b Ia, and then times the speed, which is omega m. In the other videos we saw it was usually this force times speed, but it's the same thing as saying the torque times the angular velocity. And this here would be EB times Ia, since the omega m at the bottom disappears. So this EB Ia is actually the electrical input power minus the stuff that's lost in the windings. But that's more of a side note, I guess, than anything else. So this, again, for omega m less than or equal to omega b, and this is for omega m greater than or equal to omega b. So how do we summarize all of this? If we summarize all of this, we see something that we're very familiar with, and that should bring us some comfort because it lets us know that we're doing things somewhat properly, if not totally properly. This is omega b, this is omega m, this is, I guess you can call this voltage or whatever you'd like to call it. I'm not going to put any label on this side because the numbers are different. I mean, the quantities are different, right? So it's power and torque, I guess you can say, or units that are proportional to power and torque. But in this case, it's not, because it's this one. This plot is going to be different. So this one's going to have a force, sorry, I guess a voltage, I should say. And I've drawn this incorrectly, so this should go higher up. Well, it doesn't really matter because remember we said that these are not proportional, but I guess I'm just following my notes here. And then you have this here. I guess technically this is correct since this would be the lower value, because we're saying this red is VA and we're saying that this blue is EB divided by omega m, and this this thing here is the rated EMF, and this thing here is the rated EMF divided by the rated speed. And this thing is analogous to, and you can kind of make the connection, but based on all the equations or I guess the equations and the relationships we've shown above, you can show that this is directly analogous to the following situation, which is that the power, let's say, increases like this, constant after, so this is power. Let's call it PM because we've used the variable there, so it's not just some generic power anymore. It is now PM, and this would be your torque, TM, and I apologize if my lines are not very neatly drawn. I have to twist and turn my tablet. Sometimes it's limited in its rotational capabilities due to the mess that is on my desk. Anyhow, this would be some PM max, I guess, and this would be omega B here. And we can call this side the constant torque, because the torque is constant, and this is obviously constant power. And the same applies to the other one here too. So this is also constant power, and this is constant torque. So we see that we have achieved basically the exact same characteristic, right? But since we can't control k phi directly, you have to control it through IF. And you can basically then translate the k phi omega m curve to be an IF omega m curve. I'm not going to show that here, but it's just something to note. Something else that you should also understand is that these k phi IF or these magnetization curves are usually determined experimentally, and they can be programmed into like a lookup table and used for practical things. So if you're actually trying to build one of these things, you'll need some type of magnetization curve. In some cases, you can actually find the curves available online, maybe in some data, in some tables or something that you can program. But essentially what we're going to say is that all that aside, if the magnetic material of the machine is not driven into saturation, we know that it's approximated by a line, and we said that it's approximated by k phi equals kf if, right? So we've seen this expression before, and this is in the linear region, and you can adjust this according to the set point, right? So for instance, I mean, if we were going to implement this as in a block diagram type of format, and we'll look at the complete block diagram later, but if we wanted to implement this, you can set the field the field current set point by doing something like this. So if you have this block, you have another block, and then let's say you have this, and so let's say this is your IF reference, and this would be your mechanical speed, or your machine speed. This would be k phi, reference for k phi. This would be your magnetization curve, I guess we can call it. Let's call it the mag curve. And this would be the field weakening sort of profile that you need, right? So based on these, you'd be able to determine what your k phi should be, and then this would be your magnetization curve. If you're assuming that it's linear, this can be replaced by 1 over kf, just a constant block, right? Because you don't need, if you assume it's a linear relationship, you don't need to program an entire curve in there. You can just use a 1 over kf block. Similarly, I mean, if we're going to talk about the field current, why don't we just briefly touch on the armature current control, I guess, the set point for that, because yes, we control the armature voltage, but we do that through the armature current usually. So the VA and the EB and all that kind of stuff is usually controlled using IA. So it's IA and IF that are the control variables, not VA directly. So the set point for the armature current we can determine by a torque command. So it's a similar type of idea, I guess, where you have a command comes in, you have a second thing, and then you have a limiter, I guess, because it's a good idea to have one of those. So this is IA star, the reference for the armature current. This we can call TM star. This thing in here we can call 1 over k phi b. So that's the rated value. You can replace with omega b over EB if you'd like instead. And this block here is just a limiter, so it's a saturation block so that you don't exceed the rated values and burn your machine or damage your machine somehow. So we can call this a limiter. And the saturation block, essentially. And saturation blocks are usually shown with something like this, although they're usually done a bit neater, so why don't we try to do something. something like that. So Tm star is the tractive torque desired in the constant torque region. So when you're in the constant torque region, which is this region, that's the Tm star that you give to this, and then your control should be able to adjust for other situations. So one last thing I guess we can look at is, well, not last thing for this video, I guess we can conclude this video by looking at how we can express the torque, or the command for the torque, as a fraction of the rated torque, right? So what we're going to do is, and we've defined this, I think we've discussed this idea of this parameter x theta m before. And if we haven't, then we can discuss it here. So we can basically define a parameter, and we can call this parameter x theta m, and this is defined as the set point divided by the rated value. And we say that this is between plus and minus 1. So that'll be minus 1 x theta m less than equal to 1. And this implies that this goes between your set point, which makes sense, goes between your the positive and the negative, that should be TMB, positive and the negative rated torque. So you're obviously your machine set point should not be larger than your rated value. Otherwise you can't operate. I mean, how could you ever hope to do that, right? So practically speaking, you can imagine that this x theta m is like your acceleration pedal. So how much are you demanding from it? Are you demanding it to go all the way to 1, or are you demanding it to be 0? Or I guess negative would be if you switched gears and went into reverse, right? That would be the negative version of x theta m, because you can't just, there's not a reverse pedal, or your pedal can't reverse without changing the gear. So based on this formulation, we can do the following. I guess the last little thing we can touch on is this expression, is Tm being equal to x theta m tb, and this is x theta m, I guess we can say it's tb times omega b over omega m, and this is for omega m less than or equal to omega b, and this is for omega m greater than or equal to omega b. And alternatively, I guess these two, this one is the power expressed as this x theta m. So in case you need the power requirements, you would have PB divided by omega b times omega m, and then you have x theta m PB, and again these conditions are omega m less than equal to omega b, or omega m greater than or equal to omega b. And I can summarize this last little bit that we've done here with the following curve, which is a very useful and a more elaborate version of the thing we've been looking at so far. So if this is omega b, this whole thing is omega m, and we have two different things here again. We have something that does something like this. We have this curve here, which is constant power on the right side, and then we have constant torque here, right? So constant torque here, and then this drops off like that. Now, what are these maximum values? The maximum values are what's kind of important in this case, because that's why we redrew these. This is now x theta m p b, and this is now x theta m t m b. Right? So now these are what they should be in the constant regions, right? So you can control those, and then the rest of it will still fall off as it should. So you can control how much you're giving in the maximum case, and this profile will basically shift up and down based on the command that you give it. So what did we really do here? I think we looked at a fair bit of stuff. I mean, a lot of it was just going back and forth between these, relating the machine parameters. So these are DC machine parameters that we've looked at. And we've established then that we can sort of, if we can force the flux to follow this characteristic, then we can have all the following. So we're saying that let's have the flux be this value, let's have it be its rated value for these speeds, and then let's adjust it when it gets higher. If we impose this condition, then we see all of the following starts to happen. This is a very good condition, we said, because remember, that means that the armature voltage is fixed at the rated EMF. Again, this was in ignoring the winding resistance. Otherwise, it'll be slightly larger, depending on the current. Then we said we can have a torque that follows this condition. We can have a power that follows this condition. And then we related this is basically the DC machine characteristics. And we see that they basically give us the exact same characteristic as the vehicle profile that we want to achieve, just based on these conditions that we've imposed here. So then we looked at these rough little control models, I guess. We'll look at a detailed full control model of the DC machine in an upcoming video. But for now, I mean, this is just a sort of process as to how you can achieve these different things based on the stuff we've discussed so far. So in the upcoming videos, like I said, we'll discuss how to actually control the currents, the models that we can use to do all these things. And then finally, we introduced this parameter called x theta m, officially introduced. I think we introduced it in a previous video informally to just say that we can do some stuff. And then we finally arrived at this characteristic, which is adjustable, which is a very convenient thing to do. And again, we'll look at how to control this later at some point. So I hope this was helpful. Like and subscribe to support the channel. If you have any questions, leave them in the comments below, and we'll see you in the next one.